Hello, my name is Abraham George, and today I'm going to talk about hydrostatic tube bending. Specifically, I'm going to discuss how this new technology works, what its market is, and how it stacks up to its older counterparts. Before I dive into what hydrostatic tube bending is, I want to discuss the market for this new technology. Tube bending classically can be broken up into two main sections. The installation of pipes, such as in the plumbing and electrical field, and the creation of parts, usually in a structural context, often on an industrial scale. The hydrostatic tube bender mainly focuses on this second subgenre, the structural tube bending, because it's best suited for industrial uses. An example of this type of tube bending is, for instance, the creation of this dirt buggy that you can see in the bottom right-hand corner of the slide. So let's quickly review the types of conventional tube bending, and then how they relate to the new hydrostatic tube bender. So conventional tube bending breaks down into three main categories: compression, drawing, and rolling. Compression is the simplest form of tube bending. It's the most common on a small scale. Simply, you place a tube on a die and compress both ends of it to bend the tube around the die. Oftentimes this is used in hand-sized tube benders. The second type of tube bending, drawing, is similar to compression, but rather than only using compressive forces, it grabs onto the tube and pulls it around a die. This is draw bending because it draws it around the die. And finally, rolling. And compressive and drawing, those are classical tube bending types that the hydrostatic tube bending isn't very similar. Rather, hydrostatic tube bending is much closer to rolling. And the way rolling works is it bends a tube by passing it through a system of rollers. And just a quick note, this is best for large radius bends due to just the size restrictions of those rollers. Now there are some issues with conventional tube bending. Once again, the basic ideas of this is to put pressure around a die in order to bend the tube. And whenever we do approach tube bending this way, oftentimes we get deformations in the walls of the tube. For example, if the outer wall is too thin, the pipe can collapse inwards, and one way to fix this is by using a pipe filler, which is called a mandrel. Additionally, the interior wall can wrinkle. This is classically solved using a whipper die. However, both of these problems can be eliminated potentially using hydrostatic tube bending. Additionally, in order to bend a tube, the tube has to be able to deform the amount required in order to bend it without cracking or breaking. This can be a significant issue with more brittle materials, and once again is something that the hydrostatic tube bender addresses. So now that I've finished with the preamble, let's get into what hydrostatic tube bending actually is. So the way hydrostatic tube bending works is very similar to hydrostatic drawing using dies. The concept is you pass your tube through a set of dies or rollers, very similar to the rolling tube bending, but you do the process while under intense hydrostatic pressure. The reason we use intense hydrostatic pressure is to put all parts of the pipe in compression. This act can help reduce defects and unwanted deformations, because rather than some parts of the pipe being in tension, some parts being in compression, all aspects of the material are in compression. That's the basics of it, very similar to rolling bending, except using that high pressure hydrostatic fluid. Okay, so I've alluded to it a bit before, but let's go over what the pros and cons of hydrostatic tube bending are. I'll really hammer out what these advantages and disadvantages are. So the first advantage of hydrostatic tube bending is that those surrounding compressive forces that the hydrostatic fluid exert can help decrease the chance of defects such as cracking. This is especially useful with brittle materials which respond much better to compressive forces than to tension forces. What this means in a more practical sense is it increases the number of materials that can be bent. Brittle metals, which previously couldn't be bent because of the high tension that they would have to withstand, now can be due to the compressive nature of hydrostatic tube bending. So it opens up a wide range of new materials. However, there are many disadvantages to this setup. First and foremost, it requires extensive high-strength castings to contain this hydrostatic fluid. You have to compress the fluid and you have to contain the fluid. And this setup can be quite expensive compared to the standard conventional means of tube bending. Additionally, having this high-pressure fluid increases maintenance costs. The high-pressure seams that are required to keep this fluid contained can be very expensive to maintain and have to be maintained properly, or else they might burst. Additionally, the fact that all of the moving parts are encased limits access and makes routine maintenance much more difficult. Finally, let's discuss the implementation and manufacturing readiness of the hydrostatic tube bender. Beginning with implementation, where would this new technology best be placed in an industrial setting? The benefits of the hydrostatic tube bender are best suited to an implementation in a large-scale manufacturing facility that specializes in high-quality parts made of specialized materials. This is because the extra cost of using the hydrostatic tube bender can be offset by its ability to create parts with fewer deformations made out of more specialized materials, such as materials that do not take well to being placed in tension. A good example of this setup would be making titanium parts for aerospace applications. In this situation, the extra cost of the manufacturing process is offset by the extreme value of the parts it can create, and its ability to create parts out of specialized materials with low deformations is exceptionally important. Now let's discuss the manufacturing readiness of this technology. I would argue that the hydrostatic tube bender is approximately an 8 out of 10 on the manufacturing readiness scale. At this point, pilot capabilities have been shown, but it is not quite ready to do high-paced manufacturing. It is useful for low-rate processes, but is not quite to the large industrial scale that would describe a product that is ready for mass market adoption. Thank you very much for your time. I hope you've enjoyed this presentation on hydrostatic tube bending, covering how this procedure works, what the market for this procedure is, what benefits it gives, and the implementation and manufacturing readiness of this technology.